Awesome. Well, thanks everyone for coming out. I'm Michael Kaplan. I'm an engineer on the Ava Labs team, and I'm here to talk with you all today about Avalanche Warp Messaging, which is our solution for subnet interoperability that we've been developing for the past 9 months or so. Before I go into Warp Messaging, though, I want to take a quick step back to recap what we have been working on for the past year. So last year at Summit, we announced that we are going to launch the new core wallet, and with it, the Bitcoin Bridge. And the goal of the Bitcoin Bridge was to allow users to move their Bitcoin onto Avalanche to be able to use it in all of the DeFi applications within the Avalanche ecosystem that they didn't have access to on the Bitcoin network itself. And this bridge was built using the same architecture as the Avalanche Bridge that connects Ethereum to Avalanche that launched in 2021. So we were able to launch this bridge last summer, and it's within the core wallet, and we've seen kind of steady adoption even throughout the downturns in the market, which have been super exciting to kind of see that traction grow organically despite the market conditions. So there's roughly a little over $160 million worth of Bitcoin that has been moved to Avalanche. There's actually more Bitcoin bridged over to Avalanche than in the Lightning Network, which was exciting to pass, especially just within the first year of the bridge. And one other cool aspect or statistic there is that there's almost 200,000 addresses that have held BTC.B on Avalanche, and we hope to see that number grow significantly into the future. So what sets the Avalanche Bridge apart? Just as a final slide of what we were working on before Warp Messaging. Well, one, it was built with a security-first mindset. So we took a very narrow approach to only wanting to enable secure, efficient, and intuitive asset transfers into the Avalanche ecosystem from external blockchains. And that's very different than subnet interoperability, which I'll get into a bit. So it has a very strong set of bridge nodes that validate each transfer across the chain. Those partners within the blockchain space span across security firms, to explorers, to infrastructure providers. So a very diverse set of knowledgeable and reputable companies. And the fact that it uses SGX technology not only helps make it more secure, but also allows us to think of the bridge kind of as an off-chain smart contract, where the smart contract logic isn't executing on-chain, but it's executing within a secure, trusted enclave. And since the logic is actually executed off-chain, it removes the need to have that smart contract logic be available on-chain. So for a chain like Bitcoin, we can build this bridge such that 6 of 8 partners need to approve each transfer across the bridge, even though we can't express that logic in a smart contract because Bitcoin doesn't have smart contracts. So it's VM extendable in that sense, which allowed us to extend the Avalanche Bridge architecture that we used for Ethereum over to Bitcoin and allow people to bring the Bitcoin in. So right around the time we were launching the Bitcoin Bridge, I got a few questions if we could take this great bridging technology that we built to allow people to move their liquidity onto Avalanche from external chains and apply it to this great technology that we built called subnets in order to scale blockchains horizontally within the Avalanche ecosystem. And it's kind of a very natural question to ask, given that we had built these two technologies, but unfortunately the answer is absolutely not. All of the features that make the bridge secure and efficient for the use case that it was designed for, limit it in the sense of how we could apply it to make subnets generally interoperable. And so once we realized that very quickly, we kind of went back to the drawing board and thought about what we needed in terms of subnet interoperability within Avalanche. And that's where we really started getting into the design of Avalanche Warp Messaging. So what were our goals for subnet interoperability? Well, one, the solution should not rely on any additional set of trusted parties or validators. So typical blockchain bridges have some set of bridge nodes that validate the transfers across the bridge. I highlighted the ones that are our partners for securing the Avalanche Bridge that are really required because of the fact that the blockchains that they connect, Avalanche, Ethereum, and Bitcoin in this case, have no idea of each other's existence. They have no idea of the transactions that are occurring on the opposite chains, and they have no idea who the validators of the other chains are. So within the Avalanche blockchains, whether it's the primary network or subnet, you don't know the state of Ethereum at any point in time, which is why we need this external set of validators to provide that information on-chain for either side of the bridge. But we don't want to do that in this case for subnets because all subnet validators validate the Avalanche primary network, which consists of the X, C, and P chains. And most importantly, in this case, the P chain, where all of the validators are registered for all subnets. So every subnet validator knows of each other's existence, even though that they don't know about the state of another subnet. So throughout the presentation, I'll refer to an example of doing a cross-chain transfer from subnet A to subnet B. Those two subnets, despite the fact that they don't know when a transaction occurs on one or the other or what the state of the other chain is, they do know of the validator set of their opposite subnet they're receiving or sending messages from. Another requirement for the interoperability solution is that it should scale easily with the number of subnets. So we really want to encourage and enable anyone to come into Avalanche and launch their own subnet, have a full suite of supported functionality, not just having their own application chain, but being able to connect it very easily to any other chain within the ecosystem to bring in tokens, to bring in liquidity, and launch more easily. And with that as a requirement, we also can't rely on these bridge validator nodes because they would need to kind of act as gatekeepers, standing up new infrastructure to support those transfers. So we didn't want to require that. And then finally, the solution should be fast and cost effective. This one's relatively self-explanatory. You're going to have to pay something for a transaction on any blockchain. If you're doing a cross-chain transfer, it consists of two transactions, one on the sending chain, one on the receiving chain, and it should have a reasonable gas cost. Obviously, if you're performing more computation within those transactions, they might be a bit more expensive, but on the whole, the price should be relatively inexpensive. And the latency should only be limited by block confirmation times. So since you need to have these two transactions, you're somewhat inherently limited by the fact that you need to send the transaction on subnet A. That transaction needs to get included in a block and finalized, and then that message that was included in the transaction needs to be delivered within a transaction on subnet B, and that needs to then be included in a block and be finalized. So we are somewhat bounded by a bottleneck here of 2 block confirmation times. That's an inherent limit of any cross-chain system, except within subnets, block confirmation times can be arbitrarily fast. So we also didn't want to add any additional bottleneck on top of that. We should be able to go as fast as the blockchains are going. And just to give you all a sense of why those 3 things are important for applying them to subnets, I think this diagram was shown, or this visualization rather, was shown in a few different presentations yesterday, but it's a visualization of the current subnets that were deployed or created on the Fuji testnet, and obviously there's a good number of them, and it would take a lot of time to stand up infrastructure to draw dots in between each of these subnets. So you can kind of just get a sense of why it's important that we have a solution where if you're launching a new subnet and you're adding a new cluster to this visualization, you can draw those lines and connect your subnet to other subnets natively without needing any additional parties to perform any action. Great, so that sets the stage for Avalanche Warp Messaging, which is the solution that we designed. I see Patrick smiling in the back because this is the diagram that he put together for it. There's a lot in the diagram, and I'm going to do my best to kind of walk through it at each stage, not just to talk about how we implemented it, but to also give a little bit of insight into why we made the design decisions that we did. So Avalanche Warp Messaging at its core is a primitive that allows for subnets to authenticate messages from one another. And subnets independently define the verification criteria for receiving messages from others. So if we go back to the visualization, if you're spinning up a new subnet, you might have an application where security is first and foremost a priority, and nothing else really matters after that. And in that situation, you would want to have a higher threshold for the criteria to verify that you received a message from some other subnet, or you might not want to receive messages from other subnets at all, or you might want to only receive them from a small subset of subnets or the primary network. But on the other end of that spectrum, you could think of a hypothetical subnet application that wants to receive all messages sent by all subnets at any point in time. And they don't really care how many validators signed it or participated in its verification. So we wanted to provide the flexibility for subnets to be able to define those parameters themselves within Warp Messaging. So starting to dive in here a bit into this diagram. Step number 1 and 2, first the validators register their BLS public keys on the P chain. So this is the validator creation process that you have to go through really for any proof of stake network you register as a validator. But now in Avalanche, when you do so, you actually prove that you own a BLS public key. BLS is the cryptographic signature scheme that we really use to power Avalanche Warp Messaging at its core. It's similar to any other signature scheme like ECDSA that's used in Avalanche. Bitcoin and Ethereum, very common throughout the blockchain space. But one of the primary reasons why we chose to use BLS here rather than any other signature scheme is that BLS allows for signature aggregation. So what that means, typically, if in ECDSA, for example, if I want to prove to you that both Alice and Bob signed a message, I need to provide you with 2 signatures, one from each Alice and Bob, and you need to verify them independently. So that grows linearly with the number of participants in that signature or multi-signature. And in BLS, in contrast, you can combine the signatures into one or aggregate them, really just performing addition. You add Alice's signature to Bob's signature. The result is a single signature that you can verify was constructed by using both Alice's and Bob's keys. So that compacts the signatures down very nicely. Obviously, there are trade-offs to using BLS versus a threshold signature scheme or any other type of cool cryptography we could have gotten into, but I won't go into that now. Happy to talk about it afterwards if anyone has questions. So just to touch a little bit more on number 2 here, when you're sending a cross-chain transfer from subnet A to subnet B, the first step is that the transaction containing that message is sent on subnet A and gets finalized on that blockchain. When that occurs within Warp Messaging, it lets the validators of subnet A know that they should be willing to sign this message to be delivered to its destination. So it's really just an indication that this message was submitted on chain and it was finalized in a block, so now the validators are willing to sign that message. And they sign the message using the private key that corresponds to the BLS public key that they registered in step 1 on the P chain. And because it's registered on the P chain, all validators of the Avalanche network, no matter which subnets they're validating, can actually verify that signature. So then once the transaction is sent on subnet A and all of the validators of subnet A are willing to sign that message, we need to then collect a sufficient number of those signatures to represent a certificate of a threshold of subnet A's stake in order to prove to the other subnet that this message was in fact finalized on the origin chain, and we prove it by providing this aggregate BLS signature from the validators of subnet A. So how does that happen? How do we actually get these signatures, aggregate them, and send them to the destination? Well, that is where the Warp relayer comes in. So the relayer is an application that we developed to support the flow of messages within Warp Messaging, and it really just follows this same flow on the right there for any arbitrary warp message between any subnets. So it doesn't matter what virtual machine those subnets are running, what the message format is, they all follow that same type of flow. It starts off by first establishing connections to the peers of the origin subnet in order to be able to one, listen for new messages, you subscribe to be notified of when new messages are actually submitted and finalized on the origin chain. And then 2, to be able to query the validators of that subnet for their signatures. So the relayer, just to start from the top, is listening for new messages on the origin. When it sees a new message, it queries the validators of that origin subnet for their BLS signatures. And then it performs this BLS signature aggregation, which you can really just think of as addition of those signatures. And then at that point, it has the raw message and a certificate of that message in the form of this aggregate BLS signature. And it puts those two things into a transaction to be sent on the destination chain. And the relayer is actually the application sending that transaction itself on the destination chain. I'm sure most of you are familiar with how transaction fees work in blockchains. That means that the relayer is fronting the transaction fee on the destination because it is the one actually sending the transaction. That includes the signed message. So there's a few different ways that we envision the relayer being deployed to kind of account for the fact that they need to front this transaction fee. One, it's important to note that anyone can run an AWM relayer. You only need a single relayer to deliver your message, even though there might be multiple relayers running or even racing to try to deliver any given message. If you'd like to run your own relayer, you're more than capable of doing so. There's no permission set up in this model. So anyone can run their own relayer, and if you're doing so, you can also deliver your own message because you are obviously kind of self-incentivized to do so. If you're the one sending the message, you certainly want it to be delivered. So you can just pay that transaction fee to deliver the message yourself. Another model we envision is that projects might want to just run the relayers to support users to come into their new subnet or new application that they built because they can front those costs on their own subnet and they want to acquire those users, so they'll just kind of front those fees if they would like. Or finally, we could also have it such that when you submit the message, you provide a tip to the relayer who delivers the message. So when the message is submitted, you kind of lock up a small amount saying whatever relayer delivers this message is able to redeem this tip that I'm providing. And that way the relayers are directly incentivized for each message to perform this function of aggregating the signatures and sending it in a transaction on the destination. Great, so we went through steps 1, 2, and 3. Now, to just touch a little bit more upon how we validate the messages in the destination chain once we get there. So this portion is actually what Aaron Buchwald is going to talk about in 2 hours right here. So I highly recommend you come back for that talk. But at a high level, it requires actually looking up the p-chain state there in number 4, and then actually just performing the BLS signature verification. Patrick did a lot of work to enable new VMs developed with the HyperSDK to kind of implement steps 4 and 5 very easily with out-of-the-box library support. We also worked to implement steps 4 and 5 within the EVM because that's so widely used for the existing chains today. So that's what Aaron's talk will be about. There's a lot of interesting technical challenges there. So that touches upon steps 1 through 5 and really kind of wraps up warp messaging. But the next part I wanted to talk about really quick was what the messages mean once they get to the destination. The messages are just authenticated arrays of bytes, and in order for those bytes to have any effect on the destination, they need to be interpreted and actually executed on the destination chain, and that's where Teleporter comes in. So Nick introduced Teleporter in his talk yesterday on the mainnet stage, but it's a messaging protocol built on top of Avalanche Warp Messaging within the EVM that enables cross-chain smart contract invocation. So if you're a application developer that launches your app on one subnet, you can launch a smart contract on that subnet that directly invokes a smart contract on any other EVM-based subnet, including the C chain, since the C chain is an instance of the EVM. Why we need Teleporter? Well, one, it provides a retry mechanism to guarantee that messages can be delivered even in the event of extreme validator set turnover. It provides message execution, which is what I was saying is the interpretation of those authenticated messages to actually have the desired effect that you want them to have on the destination chain. Teleporter provides replay protection to ensure that messages can't be delivered multiple times. That's not something that's guaranteed by Warp. And then finally, Teleporter is also where we implemented the incentivization mechanism so you can give a tip to relayers who deliver your messages. I have a brief diagram of how the cross-chain flow goes from one smart contract running on subnet A to the other on subnet B, but I'll skip it just for the sake of time. Happy to go into more detail afterwards. But what do want to call out, the portion I included here in that yellow box is kind of all of what Warp and Teleporter offer you out of the box, so that as smart contract developers, when you're writing your smart chain applications, all you need to worry about is specifying the end application on the other side of the box that you're actually invoking. You don't need to worry about anything of the message authentication in the middle or how those messages are interpreted. That's all provided to you within Solidity, which is pretty nice. And then very briefly, just a example of kind of a cross-chain smart contract and how that could be implemented. So you can see here, for those familiar with Solidity, we just have a receive block hash method on the destination chain that would be deployed. This is publishing the block hash of one EVM chain to another EVM chain, which you could then use to prove other things about the EVM state. So we have the contract on the destination to receive the block hash from the origin. And then on the origin, you can see we're just encoding a call to this method. So if you are a smart contract developer or have worked with bridges before, hopefully this is super exciting to you because it enables you to invoke those smart contracts across multiple chains. If you're not, this probably looks super complicated, which is also correct. The next step here is really to abstract more away so that really you don't even need to worry about the fact that it's a cross-chain operation you're performing at all, right? Within the US mailing system, when you put a letter in the mail, you don't need to think if it's a cross-state letter or not. You just put the address and you put the state that it's going to. It should be similar for cross-chain operations within blockchains. If you're trying to transfer tokens and you are transferring tokens on another subnet, it doesn't really matter. You should just specify this is the subnet, this is the address, and the token should arrive. So there's definitely more work to be done to get to that vision that we are hoping for. And then lastly, just some future use case ideas that we've tossed around in various calls. Don't want to leak too much alpha. These aren't things we'll necessarily be doing, but are possible use cases that anyone could build on top of Warp and on top of Teleporter. Moving native tokens into subnets, so it should be super easy to use Warp or use Teleporter to launch your subnet with, say, Avax as its native token that's used to pay for transaction fees on that subnet. And it should be easy for those tokens to be moved from the primary network into your subnet and back. Cross-chain subnet, or cross-subnet governance rather, we envision the C chain kind of being a centralized place for liquidity within Avalanche, since it has the most traction today. And if you have a governance vote, it might make sense to have the actual voting take place on the C chain, since that's where all the tokens exist already. But you want the effect of that vote to have effect within your own subnet. And you can use Teleporter to kind of publish the results of the vote. Cross-subnet NFT transfers, I'm not an NFT person myself, but we've gotten enough requests to support NFTs on the Avalanche Bridge that I'm sure someone will build this eventually. And then 5 and 6 are a bit further into the future in terms of an Oracle subnet or VRF subnet. We should be able to use Warp and Teleporter kind of as a foundational piece in the Avalanche subnet ecosystem. And we envision it being used in ways that we don't know yet. We want to enable applications to be built that kind of take advantage of services offered within other subnets natively right out of the box without needing support of any other intermediaries or any other kind of permissioned setup that you need to go to someone else to set up. And I think we're very excited about what the future holds and what you all will be building on top of the platform that we offered. So that's all I had. Sorry, I went a little bit over, but thank you very much for attending. You've been a great audience, and happy to stay around and answer questions.